Here is an introduction to stellar equilibrium to accompany Chapter 16 of the textbook Astronomy from Open Stax. So what is a star? The basic definition is just a luminous, massive object where you have an inward force of gravity and that's balanced by outward pressures. That's the most generic definition that you could come up with that encompasses basically all stars. And so the best example that we have is our sun. And that's the one that we know what it looks like the most in terms of just visually and then all the details within it. And you can see that you're basically dealing with some spherical ball of gas, and it's really hot, and it's really bright. And beyond that basic definition of our luminous massive object, inward force of gravity balances outward pressures, there's a lot of different details here, and the details of the specific stars can make them be quite different. So for instance, they can vary greatly in size. So here is our sun, is a tiny dot that you can't even see in this image, and here are some other stars that are nearby that are absolutely massive. They can vary in composition. They can vary in color. So you'll notice the colors in this image are kind of the visual colors of these objects. That has to do with black body radiation that we talked about back in our introduction to light. And the other properties can vary as well, how long they will live, those kinds of things. So how does a star exist? The main principle of stellar equilibrium, of a star existing, is something called hydrostatic equilibrium. And that's just a fancy way to say that pressure and gravity are balancing. And so to describe this, we're just going to consider some chunk of our star. So I'm just taking a little chunk of it here. Down goes in the down direction. So we're going towards the center if you go down on this slide. The chunk has some mass m. There's a force of gravity on it, little g, and you have a pressure on it from the outside. This pressure could be gas pressure, it could be radiation pressure, so actual photons pushing on things. It could be something called electron degeneracy pressure, which is a quantum mechanical effect that happens when you compact matter into a small volume. So all that matters here is we have gravity and we have pressure. So from introductory physics, you've heard of Newton's second law, and this means that for any object, the net force, so this is just the sum of all the forces acting on an object, is equal to the mass of that object times its net acceleration. So if I put some force on an object, it's going to accelerate, it's going to pick up velocity increasingly with time, and that acceleration is dependent on your net force. So if we have a chunk of our star that we're going to say is static, it's not accelerating, that means that the net force is zero. And so that's what you need if you want to have equilibrium. You need your chunk of star here to just kind of stay put. If it were moving inward fast, your star would be collapsing. If it were moving outward in an accelerating way continuously, the star would be exploding. And so a stable object, a stable star is going to have the net force is going to be zero. So then if we consider the two forces that are acting on our little chunk of the stellar envelope here, or the stellar atmosphere, then we have gravity that is pulling inwards. So you can see gravity going down here in our picture. And we have pressure, and the pressure is actually acting on this object on all sides. So it's like, when you're in a swimming pool, you have pressure from water, from the fluid below, pressure above, and also on all the sides. There's just a fluid pressure. And a star is a ball of gas, and gas is fluid too. So you have pressure pushing from all sides. However, the forces in the horizontal direction in our picture are going to cancel out. So if I have some pressure on the left side of my chunk, that's going to cancel with the pressure on the right side of the chunk. These two forces are going to cancel out. Same with on the front and the back. So we don't really care about the ones that are in the horizontal direction in our diagram. We're only going to care about the force from the pressure on the top and on the bottom of the fluid element. And remember that we're in hydrostatic equilibrium. Our net force needs to be zero. So these vertical forces need the sum to be zero. So we have on the one side, we have pressure. There's a pressure force pushing up. So that's just the pressure of the fluid times the area. So that's pushing upwards. On the other side of our equation, we have the downward direction. So there's the pressure of the fluid at this height times the area of the little chunk here. That's the force down. And added to that is the force of gravity is pulling this chunk of matter towards the center of the star. These need to be equal to each other. A pressure force is just the pressure times the area. And this is familiar to you if you've ever gone to a wedding in the summer outside and you've walked on the grass. You'll notice people wearing flat-bottom shoes. They can walk just fine because their pressure is distributed over a large area. And so that, or rather their force is distributed over a large area, and so that's less pressure. If instead people who are wearing high heels or pointed shoes, their force is distributed over a small area, which creates a very large pressure. So if that example didn't make sense to you, just take my word for it, that if you take a pressure and you distribute it over some area, that gives you a force. And the force of gravity is the mass of our fluid chunk times the local gravitational acceleration that we usually call little g. So we can set these two, or we can plug these little sub-equations into our main equation here. We can do a little bit of algebra, and what do we find is that the change in pressure over the height of the fluid element, so this is the difference in pressure between the bottom and the top of the fluid element. We take that difference in pressure and divide it by the height of our chunk of our star, of our fluid element. That is equal to the density of this chunk of star times little g, the local gravitational acceleration. And if we want to convert this from an algebraic form to a differential form that we would use in calculus, then this is the same equation. Just the change in pressure with the radius of the star is equal to the density of that region of the star times the local gravitational acceleration. The upshot of this is it means that just what hydrostatic equilibrium says is that the pressure difference on the top and the bottom of a chunk of star, that pressure difference needs to be equal to the gravitational force on that chunk of the star. That needs to be satisfied for you to have hydrostatic equilibrium, for you to have a stable star. If this is not satisfied, this condition that the pressure difference needs to be equal to the gravity, then you don't have a stable object. So your star is either collapsing or exploding. Okay, so where does this mysterious pressure come from? And we can rephrase this by saying, what is providing the energy to actually power our star? So there's a few options we can think of and that people came up with when they were contemplating stars a long time ago. And when I say a long time ago, this was late 1800s is when a lot of progress was made. So one idea is gravity. So if I take an object at some high height and I drop it, right, it picks up velocity, so it converts that gravitational potential energy into kinetic energy. It can knock into another object here, so I can have one, for instance, atom knock into another atom as it falls, and it will then transfer that kinetic energy it had into this other molecule or atom here. So you can take this object that was at a further radius at a higher height, drop it, let it contract, and it will result in collisions here in the gas that is at a lower height or closer to the center of the star. And so what do these collisions do is you can heat up the environment because the velocity tells you the kinetic energy, and that's related to the temperature. Also, these collisions can directly result in atomic excitations, and then your de-excitation can result in the release of a photon. And we covered this in the Introduction to Spectra lecture. So that's one concept, is that your star is just contracting, and that gravitational energy is being converted to this temperature and these photons here. Another idea is combustion, or really just any chemical reaction. And so here you're talking about breaking or altering chemical bonds, and you can make a lot of heat from that, as you've seen when you burn wood, for instance, at a fire pit or something like that. And then another option is nuclear power. So you can have a nuclear reaction happen, and that releases a lot of energy. So let's consider these in turn. So how about gravitational power? So our star has a gravitational potential energy. So this G is a constant called Newton's G. M is the mass of the star. R is the radius of the star. So it has a total amount of potential energy just from gravity. And this is just like how you have potential energy when you're in an airplane, and when you jump out of the airplane, you fall to the earth, and you pick up speed, right? You pick up kinetic energy because you're converting that gravitational potential energy into kinetic energy. So same kind of thing. So this energy is released by contraction. If this gravitational energy powered our sun, then your sun's luminosity basically tells you the rate that energy is being consumed. Okay, so you can calculate how much time would it take for me to just burn through all this energy. So you'd have the total amount of energy that's in your star from gravitational binding energy, given by the equation up here approximately. You divide that by the luminosity. This is the rate that you're consuming the energy, and that gives you then a time. And so we have our equation for this thing called the Kelvin-Helmholtz time. So if we just plug in the mass of the sun, the radius of the sun, the luminosity of the sun, if we're careful with all our units, then we get that this Kelvin-Helmholtz timescale is about 30 million years, which sounds like a long time, but that's way too short, right? We have radiological and geologic evidence that tells us that the Earth itself and the solar system is, 4.5 billion years or so old. So that cannot work. The sun cannot have been powered by gravitational energy. It would have ran out of energy way too long ago. Nonetheless, this time scale is still really interesting. This is actually tells us something about star formation. So this Kelvin-Helmholtz time is the time that it takes to go from something that we'd call a protostar, so a stable cloud of gas, into an actual star, so something that has nuclear burning going on at the core. And this diagram on the right, you don't really need to know exactly what it means, but you basically have the luminosity of a star versus the temperature on something that's kind of like a Hertzsprung-Russell diagram. And each of these lines, we're following the contraction of a given protostar, and then there are time scales here. And you can see this is our Kelvin-Helmholtz time, roughly, so millions of years. So we need to go on to option number 2. It's not gravitational power. What about chemical power? So, chemical reactions, you can get a lot of energy out of those if you have enough fuel. It's enough to get your car across the country. It's enough to power an entire city. So why not? Maybe the sun could be powered by chemical reactions. So where does the energy come from? It comes from breaking and also altering bonds between atoms. So if we think of a molecule here as, for instance, chlorine and hydrogen connected by a spring, so the chemical binding energy we're going to represent with a spring kind of potential energy, then there's a certain amount of energy just stored in these two being bound together. So we can look at the energy versus the separation of these two objects, and mostly they're going to be pretty well bound together. So there's a lot of energy here that in principle can be freed if you break this bond. You can take that energy and do something else with it. But when you look at the amount of energy that you're talking about, it's not that much. It's on the order of an electron volt. And in SI units, that's like 10 to the minus 19 joules. It's not very much energy. And we can see how little it is. So the sun's luminosity, we know what that is. It's about 10 to the 34 watts. That's 10 to the 34 joules per second. And if we do some rounding, we see that that's about 10 to the 45 electron volts per second. So, a huge energy output compared to how much energy we're talking per reaction. Now, also, we know the mass of the sun. We know the mass of a proton, for instance. And so we can say that the sun has somewhere around 10 to the 57 atomic nuclei, just ballpark. if we just make the approximation, we're going to say that all of the nuclei in the sun are atoms. So that means they have, electrons to them, and all of these have atomic bonds. This is not true at all, but let's just pretend it is, because this will give us the maximum amount of energy that we can get from our chemical burning. So let's say that all the nuclei in the sun, atomic nuclei, are in atoms. We're going to break all of the bonds. How much energy do we get out to power the sun? So this chemical timescale is the number of atoms that we have multiplied by the energy that you have per bond. So that's 10 to the 57 atoms. We're going to say that we have around an electron volt per atomic bond. And we divide this by the luminosity of the sun, so the rate that the energy is being burnt through. And we get something around 10 to the 12 seconds. It sounds like a big number, but that's only 32,000 years. That's obviously not long enough. You could be quite the science denier, and it would be hard to deny that we have hominid skulls that are 6 million years old, right? So the Earth's been around for at least that. Even if you don't trust geology, you can do radiological dating and figure out that, that 32,000 years just doesn't cut it. It's not even close. So it can't be chemical energy powering the sun. So then you got to turn to the big guns, nuclear power. So the line of argumentation here is basically the same. We're just swapping in nuclei for atoms. So we're dealing with nuclear bonds and nuclear binding energy. So instead of 1 electron volt, we have about 1 million per bond. And we can then plug that number in, or our nuclear bond instead of our atomic, and we get something that's closer to 10 to the 18 seconds, which is, on the order of the lifetime of the universe, and longer than the age of our solar system. And so that gets the job done. Nuclear power can explain the energy source of stars, and it's the only explanation actually that is available that makes any sense, the only one that can work. And all of this is really just because, nuclear energy just completely dwarfs your other forms of energy. So these are different chemical energy sources that you may be familiar with in terms of just megajoules per kilogram of that fuel. And you can look at uranium, and it's completely off the charts. So that's it. The basic summary here is that stars are a result of nuclear power creating sufficient pressure in the center of our sun, or center of a star, to balance the inward pull of gravity. And these nuclear reactions also release energy, and that's why these things are luminous, massive objects that are in a stable state, which is the definition of our star. And we'll talk more about the specific nuclear physics details in the coming lecture. That is it for this introduction to stellar equilibrium for Astronomy 1000.